Okay, so now we're ready finally to discuss what the second derivative test is for a function of two variables. The next video I'll do like an example where we apply it in practice. So the idea is that you'll have, so I will just write this down now, and in the next one I'll explain it. So you have a function f of xy, and you want to classify the critical points okay. Now, by that, it is already assumed that you found the critical points, right? And so what you will do first, as I mentioned in the video about Taylor's second order approximation, the thing is like, now when you do the second order approximation, you have like three second derivatives at play. They're different. Second derivative with respect to x twice, second derivative with respect to y twice, and the mixed partial derivative, the one that's like with respect to x with respect to y. And so that somehow is being counted twice because it doesn't matter if you do it with respect to x and then y, or y and then x. And so what you do is first you assemble all the information into a single array, which is known again as a 2x2 matrix called the Hessian of the function. So the Hessian of f, which I'll denote like this. And by that I just mean you build a 2x2 matrix where you put here the second derivative of f with respect to x, the second derivative of f with respect to y, and then the mixed derivatives in the off diagonal terms. Okay, and so suppose that P is a critical point. So it's like an x comma y where the first derivatives vanish when evaluated at this point. So what we will do is the following. So it all depends. Okay, let me write it this way. You first look at the determinant of the Hessian. You will look at the determinant of this 2x2 matrix evaluated at the critical point. So you will I'll do it in the next video. So you will compute the determinant of this matrix evaluated at the critical point. That's a number. A number can be either positive, negative, or zero, right? So let me just start with the easier cases. If it's 0, if you get 0 from this determinant, then this is the analog of when you apply the second derivative test for a function of one variable, that you got that the second derivative would vanish. Basically, you cannot say anything interesting, so the test is inconclusive here, like meaning we won't try to classify this critical point. If the determinant is negative, sorry, there was a small glitch, but since my intention here was just to explain what the second derivative says, the idea was, so you construct this matrix, you compute its determinant, evaluate it at the critical point, okay? Determinant evaluated at a critical, the determinant is this expression, by the way. Right? So you get this expression, you evaluate it at the critical point. That yields a number. A number can only be one of three things: 0, positive, or negative. If it's 0, the test is inconclusive. This is the analog of the second partial derivative being 0 at a critical point for a function of one variable. You could not just say anything else, which was interesting with this test. If the determinant, if this expression evaluated at the critical point is negative, then you get a saddle point. Okay? So this is a Pringles potato chip that I mentioned in the previous video. Now, if the determinant is positive, then this quantity no longer gives you enough information to decide what's going on. And you have to break it into two cases where you have to look at, for example, the second partial derivative of f with respect to x twice. So you evaluate this one at the critical point, and if you get if you get something positive, this is like the happy phase, so meaning that it gives you a local mean. On the other hand, if you get something negative, this is like the sad phase, meaning that you get some like a local max. And again, I'll do an example in the next video, but let me just clarify two things. If this is already positive, right? So if the determinant is positive, then that means that f of x at p cannot be 0. Right? Because if this is 0, then you get 0 minus this quantity squared, right? And this is always negative or 0, so it can never be positive, since it's not positive. So that's why we don't have to worry about this case, this third possibility. So we don't have to add it here. And the other thing that I wanted to say is that if this quantity, if this is positive, right, then if this is positive, then you add this quantity to both sides, and you get this. Right? And this is non-negative because it's the square of a number. And so that means that this product of two numbers is always non-negative. So that means that these two quantities always have the same sign. So they're either both positive or both negative. And so that's why you don't need to, you can just analyze one of the two here. Okay? So in the next video, I'll do an example so that you see what's going on more concretely.